quantitative data, like the number of options.
That's where the first question on this quiz kicks in. Here's a spinner with 10 equally spaced pieces. It's a pizza cut into 10 equally spaced slices. And you grab a slice at random. What's the chance you grab the slice with a 5 on it? Or, in this case, 1. It's 1 in 10. That's theoretical. That's theoretical. Why is it theoretical?
Because it's the actual probability.
I like that answer. I like that answer very much. It's the actual probability. That's actually a good way of thinking about it. Theoretical and experimental are both the actual probabilities. But I see what you're saying when you say actual, Crystal. You're saying you've taken a whole and split it into what?
10.
10
pieces.
Equally.
That's what I'm talking about. Equal pieces. 10 equally likely pieces to grab. So that's when you say actual, you mean like the exact, equally likely definition probability, right? It's 100% correct. 100% correct. So that, I like what you're saying when you say actual. Down here I have you simulate. I have you simulate the probability by generating 500 random numbers between 0 and 9 and then counting how many ones you get, yeah? What is that? Is that theoretical down here once you get below the beginning? Is that theoretical?
That's experimental.
That's experimental, right? Because you're running a random number simulation and keeping track of what's going on. That's where it becomes experimental. So back in the day, you guys were actually doing this weeks ago when I had you guys running that computer program, or the TI program I gave you. It was called Estimate. How many times you got to roll a die until you see all the sides at least once? How many Star Wars cards do you have to buy until you get all the cards at least once? You were doing experimental probabilities back then. You could actually calculate those theoretically directly, because we did it in class. Well, I did it for you in class. The computation's actually a pain in the ass. But you were doing experimental. That's why you collected a bunch of data and took an average. I sent you home. I think it was the first out of class exam. I sent you home, made you run the program 5 times, and then put your answers on a spreadsheet. Then we averaged all those results. That sounds like we're doing all week, past couple weeks. That's all it was. That's experimental versus theoretical. And I'll have a nice mix of that on the exam. I'll probably have you doing some simulations with your TI again on Monday, just because you don't have Excel in class. We have your TIs. So keep your TI handy. Shelly, if anything happens with 89, we can fix it. We'll figure it out. It should be well behaved now, I think. Maybe. But if anything, we'll figure it out if it's not. Good question. Whoever asked that about theoretical, was that Benji? Thank you. What else we got? And then give you grief. Garrett's looking good. I'm going to lock myself in just in case. I think it's been 5 minutes now. Yes. Oh, thank you too. I think it was Benji sent me an email about the link. I thought it was being helpful. It ended up not being helpful. So I sent you a link about the class survey, the SurveyMonkey survey, like 2 weeks ago. And then about a week ago, I sent you a follow-up email saying your out of class is posted, blah, blah, blah. Oh, by the way, if you didn't get the links for the survey, here they are, and I posted the wrong link for 105. So just go back to the original email. The correct link is in that one. I posted the 243 link to you guys. Apologies. It doesn't really matter, but there's going to be, I think, a question in there that's going to confuse you guys because it doesn't apply to you guys. I think it's a question about 244. You're like, what the hell? So go back to my first email about that. Sorry for all the spam you've gotten this term from me.
If I can't get my little buttons to work, can I like...
Just do it at school.
Can I write
Just do it at school. Take 5 minutes and do it at school. It's much easier that way.
5 minutes when it's a child.
Trust me, I understand.
I know, but I'm
I
old.
totally get it. That's great. I didn't have this before I had a kid.
I love that.
I'll let you. We're gonna get out of here early today, Di. We are most likely to have before. Then just run up and do it then. Bang it out real quick, okay? What else we got? Oh, Crystal, go ahead.
It's week 10.
It is.
Last day of week 10, and you sent us an email 10 minutes before class with a statistics.
I just got the contact information at the end of last week. I just found it on my desk. I'm like, okay, that's correct. Stat tutor in Redmond. Yeah, I mean, and then that student gave me the information that dropped my class. I'm like, oh, okay. So not that the tutor didn't drop my class, but the student that gave it to me. Apologies. What do we got? What do we got? David, go.
So is there going to be more theoretical or empirical?
I haven't decided. I kind of like mixing and matching them, like on your quiz, where I have you look at it theoretically and then have you run an experiment to kind of support the theoretical one. I'm messing around with the idea of maybe having you calculate a percent error, like we've done in the past, where you take the theoretical, take your experimental, subtract them, and then divide by the theory. And I would have that formula on the exam for you to do. So I would say, here's percent error, which I always do whenever I put them in your homework sheets. You know, actual minus estimated over actual. and then just have you run the numbers. So what I'm thinking in my head, this is kind of where my head's going with this, is running a problem like the one here, then have you generate like 100 random numbers. Then have you generate like maybe 500 or 1,000, which doesn't take all that long if you remember from your quiz. It takes a little bit of time to spit them out, but not an exorbitant amount of time. And then gather the data and then calculate the percent error each time and see what's happening to it. So kind of keeping you in a problem for a while. Does that make sense? That way you're not jumping around a lot. I tried to do it on the last exam as well, where you had Max's problem and then the Angry Birds problem. So you weren't like doing like 50 different problems, you're doing like 2 things and staying. I kind of have that idea. So I have to find a good exponential regression to talk about and then combine that with a probability problem. And I'll figure it out. We'll get there. But yeah, that's kind of the idea. I like to do a mix and match of both because you guys seem to flow back and forth between them very well. And I'd rather play the exam to your strengths. Since you seem to be okay flopping back and forth, I was like, why pick one? Just have you do both, and you can kick its ass both ways. What do we got? Great question. Great question. I haven't designed it yet. That's one of the things I want to do today is sit down and actually design the damn thing. So, what we got? What we got? How's week 10? Yeah? Is it good? Throw this up on the board. It looks like week 10 in here. I'm not gonna lie to you. Yes, looks like week 10. How are your other classes going? Good? Here's probably, oh, you can't see that. Fire the homework sheet so you can see it. Oh, this is actually a good example. And not that I would give you this kind of a question, is this theoretical or is this experimental, but you can look at the homework sheet that I'm about to show you, and you can actually tell whether or not something was experimental or theoretical based on what you're looking at. As soon as this fires up, you'll see it. I got some book problems here and some E problems. Oh, good, percent error. I can see it right there. Yay. Good. What else we got? We'll call this Ariel, go!
Little question about
Yes.
the Larson test. So,
Yes.
maybe I missed this in reading it.
It's okay.
When he says, certain percentages unlikely, percentages somewhat likely, is that based on real numbers? Or
It is. It's also based a little bit on opinion. Let's go.
Okay.
Let's go grab that, Ariel. I like what you're actually getting into a bit of a 243, 244 kind of thing. It's opening up right now.
Are we going to need a book for 243?
It's an open source like this one.
Okay.
So I mean, you can actually purchase a physical copy for like $20, but I've got everything online. You can just down. It's just like this. It's not quite as neat as this one because this one I actually have the time to chop it up into individual sections, whereas the one for 243, if I have time over the break, I'll do it and chop it into the chapters like I did here. But right now, it's just one big 700-page PDF document. Where was that?
Page 358.
358. Scrolling on down here.
It didn't seem clear to me whether or not those were like agreed upon.
That's what they are.
positions.
That's what they end up being.
Or if it was just like, arbitrary quantitative, qualitative cutoffs or quantitative measures.
Describe the likelihood of each event in words. Is that what it is?
Uh-huh.
Okay, so that I read that not so much as likely, not likely, or kind of likely, but just as what does 1 in 20 mean? What does it mean that the chance that somebody is afraid of the dark is 1 in 20? Not so much likely, that right there, FYI, this is a 243, 244 question, a great one. That's 5%. 1 in 20 is 5%. That's the cutoff that we've kind of agreed upon, and there's a very good reason for that, which we get into in 243 and 244. That's the cutoff for an unusually rare event. Anything below 5% is considered to be fairly unusual, doesn't happen all that often, and anything above 5% is considered to be usual. It's somewhat arbitrary, as Benji said, but it actually is rooted in something called error analysis and statistics, which that's what 243 and 244 spends a lot of time doing. Right now, 243 is analyzing false positives and false negatives. Like if you go to take a disease test and it comes back positive, you shouldn't immediately freak out because it might be a false positive. We're teaching them how to analyze that. Like my neighbor who, when she was pregnant, she got an amnio exam for Down syndrome. It came back positive and she flipped. And I said, Kim, sit down. Sit down, let's talk through this. And I talked her through it, through the mathematics. And it turns out, with her particular physiology, if she tests positive for Downs with an amnio exam, there's a 99.999% chance the baby is fine. And if she tests negative for Downs, there's a 99.9999, a few more % chance the baby's fine. Which makes me go, why would she even get tested in the first place if whatever result comes back is going to be fine? And the reason is because she wasn't an at-risk mother. That's the kicker. That test works great for at-risk mothers, but the problem is that healthcare practitioners won't always tell you that. They'll say, get an amnio exam.
No.
Not if you're not at risk. If you're not at risk, that does more harm than good because it comes back positive so frequently when the baby's fine that it creates, then it can actually create a problem because the mom freaks out, which can actually have an adverse effect on the developing baby. So false positives, that's error analysis, one of the error analyses. The other way is just being off because of randomness, like trying to estimate the average age of a COCC student by, for example, sampling you 25 that are here today.
No.
I'm saying I could do that and come with and call that my estimate, and that might or might not be close to the true average age. So there's error in that estimate as well, and you could adjust for that error. So 5% because of error analysis is generally a pretty well-used measure. But when he says describe the likelihood, what does 1 in 20 mean?
Oh, 1%.
Add 2 words to that, David, and I'm super happy. He says 1 out of every 20 people. Okay, here we go. Hassani, you're afraid of the dark. 7, 8, 9, 10. Boom, Daniel, you're afraid of the dark. What's wrong with that?
There's 2 people in this class that are afraid of the dark.
But I counted 20 people, and I said every 20th person is afraid of the dark.
Yeah, but that's on average.
Ah, that's the 2 words I wanted to hear. On average, it might be that everybody in this room is afraid of the dark.
Oh, God.
There we go. 1 in 20. Boom, right there. It might be that everybody in the room is or everybody in the room isn't, but what that number tells me is, whenever the study was done, of the entire study done, 5% of that study was afraid of the dark, and they've extended that out to the general population. So that's when I see 1 in 20, that's what I mean. On average, 1 in 20 people. On average, 25 out of 38 people are afraid of identity theft, as they should be. This is actually becoming ridiculous with the digital age. 36%, roughly, if you had to put that as a fraction, 36% is fine, but I would call that what as a fraction? Say it again.
1/3.
That's 1/3. Call that roughly 1 in 3 people is afraid of heights. That's interesting. 1 in 3 people. Thunder or lightning? Fraction. Fraction. 1 in 9. It's actually sort of 1 in 9. But yeah, 1 in 10, 1 in 9. Good. Good. So that I like the 1 in that, and all it means, on average, 1 in 9 people. On average, 25 out of 38 people. On average, 5% of people. That's all I'm looking at for it. As far as what is likely, what is not likely, don't worry about that. Worry more about what the interpretation of probability is. It means that on average, if I sample 1,000 people, roughly 5% of that 1,000 is going to be afraid of the dark. That's all I'm getting at with that
How
one.
come it's not 100?
Say that again?
How come it's not 100?
It could be 100 people.
Oh, okay.
I just made up a number. 5% of whoever on average, 5% should be afraid of the dark in this case. It could be 100 people, it could be 75 people, it could be 10,000 people. But it's always going to be 5% of that on average. Good question. Micah, go!
Is that the exact same theory that applies to 4 out of 5 dentists or whatever?
Probably. I've never actually seen data on that one, so I doubt. I always question that one. 80% of dentists recommend, what is it, Crest?
Yeah.
Or brushing after eating or whatever the hell it is, 4 out of 5.
Right.
I've never seen data on who they surveyed, but yeah, it's the same theory. 4 out of 5. That doesn't mean if you go to Bend and you find 5 dentists and ask them, that 4 of the 5 of them are going to go, yes, you should brush, and the 5th one's going to go, no, you shouldn't. It's kind of like, 2 out of 3 people suffer from hernias. Does that mean 1 out of 3 people enjoy it? No, it means that on average, out of 3 people, 2 of them have had a hernia, which I just made up, by the way, YouTube. I made that up right there. So that's all that means. It's a smooth average. It doesn't mean anything about every 5 people, every 5 dentists you grab.
So that means political polls are basically crap.
Well, no, careful. They're actually done very well. Though, why do you say they're crap?
Because usually it's a small sample space.
Okay, you guys are getting into these 243, 244 questions, which is it's fine to have a small sample. Believe it or not, if you want to get, let's say, the percentage of Americans, voting age Americans, that approve of Congress right now, I know it's 0%, but let's just suppose you're interested in figuring out what the percentage of voting age Americans that approve of Congress right now is. How many do you think you should have to survey? That's a loaded question, by the way. I didn't give you enough information.
1,000.
1,000. Vote for 1,000. Micah's going to say that's too small, isn't it?
I would say 10,000.
10,000. Okay? I've given you an incomplete picture. And here's why. There are 2 things you have to ask me, and this is, again, getting into 244 a little bit. You have to ask me, how off do you want to be? Because you're going to be off, correct? The only way you're going to know is by asking every single voting age American. So if you draw a sample, remember how we played craps in class on Monday, and our probability was off of the true probability, wasn't it? We found the chance of winning was 40%. It should have been closer to 49.2%. That's called sampling error. That's the error analysis I was talking about. We were off by 9%, which is completely acceptable with 200 trials. Completely acceptable. The way you get smaller error is by increasing your number of trials. So if we went from 1,000 to 10,000, we'd have a smaller, what's called a margin of error. So the first question you have to ask is, how off will you allow yourself to be? How many percentage points? The standard is 3. If you look at a Gallup poll, any Gallup poll generally is a 3% margin of error. What's the president doing? Plus or minus 3%. What's this doing? Plus or minus 3%. So you have to start by saying 3% or 4% or 5% or 1%. 10,000 samples is going to get you probably closer to 1.5 or 2%, maybe even that closer to 1. Then you got to ask yourself, how confident are you going to be in your result? Remember how that 1 in 20? That means one out of 20 people are going to be afraid of the dark. The other 19 out of 20 are not. So finding a person that's afraid of the dark is getting on the rare side. Well, you can also be completely off the mark with your study, so you have to define your confidence. 244-ish, we'll get into that, 244. Once you've established both those things, 1,068 people get you 95% confidence and a 3% margin. That's all it takes. It's amazing, but you get amazingly good results with 1,068 as long as it's random. Danielle, go!
I just have to say I'm totally afraid of the dark.
That's okay! And I nailed you! Boom, it's right! I just count 20 people and I, boom, got her.
My family makes fun of me.
They should not. That's mean. Tell them I said so.
It's awesome. It's totally awesome.
It's awesome?
Yeah.
Sounds mean to me.
It's just for fun.
Oh, okay. As long as you make fun of them for some other parallel thing. Like being afraid of identity theft. Something you shouldn't be afraid of. Go, Linda.
I've been watching your videos because I haven't been here.
Yeah.
One of the things that came across to me, at the beginning of term, do you by chance like run something about, you know, how many people in the class are going to get like an A's or B's or C's or how's going to pass? Because you run things all the time.
No, I don't do that actually. I don't do that only because, probably for 2 reasons. Number one, it fluctuates too wildly with the smaller classes we have. And number 2, remember the movie Flatliners? If you remember that movie. It's an older movie now, it's from the 80s, like me. So the premise of that movie was that these medical students would kill themselves and then bring themselves back from death. And the opening scene of the movie, I remember, I always remember this, that the A&P prof, they're working on cadavers. And the prof walks in and goes, after this exam, there will be 2 A's, 4 B's, 9 C's, 4 D's, and 2 F's. And then basically walks out. And then it's left for the students to beat the crap out of themselves mentally to get the high grades. So I hate to almost put that idea in your head in the beginning to be like, oh my God, like
Well,
2 of his kids sometimes.
If you do that, because I know that you run
I do.
all the time.
There's just too much noise on that data to be meaningful. And it's kind of like the false positive on the amnio exam. If I know I'm going to get noise, and the noise could potentially infect how you think about your own performance, I'd rather not share it with you, if that makes sense. It's better not to hear about it if you can't do anything about it, or if it doesn't tell you anything useful. Okay. Yeah. And I do. What I like to do, though, I've told you guys certain statistics, like the more quizzes you do on average, there's a high correlation with grade. So the more quizzes that are turned in, generally the higher students' grades are. That's a good correlation, because that encourages you to stay current with what we're doing. I also like to correlate your exam 1 and exam 2 grade to see if there's a hop in exam 2s versus exam 1s, which there usually is. So I like to look at those things because A, they tell me something, and B, they can change behaviors in a positive way. But at the beginning of the term, when you're already terrified about a math class, that's the last thing you want to do is make it worse. So, good points. You guys are all about, who's taking 243 and 244? Good, good, holy crap, more of you than I thought. Good, very good. Almost every question you've asked today has been about those classes. Yay. You're getting there, we're ready for it. That's kind of why I designed 105 to go that route. I wanted to be a pre-stat course. Sounds like the word's getting out. What else we got in here? Oh, let me show you this too. I wanted to show you this. All right, here we go. Nobody took me up on my feel free to stop by and check it out. It's okay, you guys are busy. So, I made a simulation in your book on exercise 24, page 371, which dealt with pulling cards out of a deck. So if you have a deck of cards, pull a card out, look at the suit, mark down what it was, put it back in. Then shuffle, do it again. Pull the suit, stick it back in, pull the suit, stick it back in, shuffle each time. This is what I got. 242 hearts, 263 diamonds, 259 spades, 236 clubs. And what I want to use is, I want to estimate the probability. First of all, first question, how many cards did I draw in this experiment? How many cards did I draw in this experiment? Estimate it, first of all. Estimate. No, don't give me the exact answer right away.
900.
900, good estimate, very good estimate. Micah, 1,000, another good estimate. 1,000, good estimates, good. I like them all because they're all about 250, aren't they? So you call them 250 across the board, that's 1,000. I think it ends up being, I think I stopped it at literally 1,000, I think. So 900 is a perfectly fine estimate for that. Good, I think I used 1,000 because I wanted you to have a nice number to divide by when you do the probabilities. Because I think later on I then say, what is the percent error for each experimental probability? Okay, so boom, what is the experimental probability of getting a heart? Well, that's a theoretical probability, is 1 in 4, isn't it? Because we know there are 4 equally likely suits in a deck, because there's just as many hearts as diamonds, as clubs, as spades. But in my experiment, 242 out of 1,000, which is 24.2%, which is pretty damn close to 25%. 26.3%, pretty damn close to 25. Almost 26%, pretty damn close to 25. And there's approximately 24%, pretty damn close to 25. And the error is going to be very, very small on these. And the error is going to get even smaller the more cards you pull and look at. What's interesting, and you guys remember this when we did it in class with the die rolls, how I had Excel rolling dice for me, and we watched the graph kind of developing, watching evolution, I believe is what Nick said. And then we turned the screen off and I left the stapler on F9, and we kept talking about other stuff and then came back. And when we came back, the graph was almost perfectly shaped the way it should have been theoretically. And that's the beauty. Now some people are going to ask me, what's the point of doing that? If you can get the theoretical probability, why go through the experiment? And that's a great question. What's my response to that? How many of you dressed because you heard it was going to be cold this morning? Yes? Well, I'm assuming you dressed because you want to get arrested when you walk out of your house. How many of you dressed properly for the weather this morning? There we go, good. Where did you turn to get the weather? Just out of curiosity. Where do you get your weather from? Your phone? The phone, yes? Z21?
Either by phone or by TV.
By phone or by TV?
Knowledge of yesterday.
Knowledge of yesterday, making the assumption it's going to be the same today.
Just look out the window.
Well, that's tricky because the sun's out.
Walk outside.
The sun is actually very brightly out right now, that's deceiving in bed. It can be very, very, very bright and be negative 10.
Thermometer hanging from a tree.
Thermometer hanging from a tree. Good data. Good data. Good data. I got my little weather station on the kitchen counter. Oh, 5. Better put my pants on today. As opposed to my shorts. Sorry, I'm around naked. So, now the question is, where does that... So last night, when you were saying, okay, it's going to be 5 degrees tomorrow, how do they know that? Where's the die they're rolling? So it's that mind reader thing. What's it going to do tomorrow?
There's lots of...
It's a roulette wheel. What's it going to do?
It's
gonna be rainy.
21 said I ran the simulations over and over and over again, and they all came out different.
Did
So
he actually
I
say
don't know
that?
what the weather's going to
He
be
actually
like.
said
I
that?
heard him say that. They all came out different, so I don't know what the weather's going to be like.
It was all based on simulation. Because what I've heard, and I actually talked to the guy in Portland about this, and this was, I forget, little dude, I forget his name now, in
Okay, now
Portland.
this wasn't Bob Shaw. This was the young guy, the Knudsen guy.
I don't know him, I'm sorry, I don't know him anymore. I just get my weather from Google now, which is always disturbingly accurate. So, what I've heard is they look, and this is the guy from Portland telling me this, they look at atmospheric conditions historically. What has happened historically when the wind is out of the north, when the pressure is whatever number of millibars it is, when the relative humidity is what it is right now, 80% of the time it has been below 10 degrees. Now, how they get to 5 degrees, I'm not exactly sure, but that at least gets them in the ballpark of it's going to be damn cold. And then you get a relatively rough estimate. So the question is, there is no die to roll. There's no magic sphere to look in, try again. No, there's none of that. So in other words, these are great because we can compare these numbers to a theoretical 1/4, 1/4, 1/4, 1/4. The weather you can't. You can't compare the weather to a theoretical because there is no theoretical. It's all experimental. And that's the beauty of experimental probabilities is you can always use them. Theoretical are great when you're analyzing Vegas games, when you're analyzing, things like dice and coins and cards, and things that you can roll and spin and deal. but they suck at everything else because there is no die of life. Actuaries spend their entire lives looking at death charts. When do people die? How often do they die? And they set, it sounds morbid, but that's what they have to do because they have to then set insurance rates based on that. So in other words, they're constantly updated. We had this discussion on Monday. You don't buy a life insurance policy for life. You buy it over a term. And then they reevaluate because then you're older and you're more of a risk, on average. So that's the idea. There is no die of life. There's an experiment of life. Go, Andrew.
Aren't people that predict weather really just rolling lots of dice?
Simulation, yes, but they're rolling the dice of simulations.
Right.
But there's no die that you can look at and go, oh, there's a 1 in 10 chance it's going to be cold tomorrow.
Well,
they have to go do the simulations to figure that out.
Because when they were doing the track for like
Hurricanes, great example.
like it was the most accurate they'd ever been before on where it was going to go.
Right, and the trick with that is you got to discount some of that as just dumb luck. You have to. They will never say that.
But the computers are stronger and they make more calculations.
No, but you're correct. You are correct. But you got to remember all the ifs they're throwing into those computers. And you also have to remember, they get more than one track on those hurricanes. Maybe one of them got really, really close to what it actually did, but they just show the other 7 that didn't.
There was most of the
And every
tracks
couple
that
of
they
days.
did.
Sure.
Every couple of days they see, because hurricanes travel as anything.
And they have to redo the track based on the new data. And that's what it is. Andrew, you're correct. They're always rolling dice.
They make the best fit line.
Or whatever curve, whatever trajectory they usually have. Exactly.
First couple of
But it's all about refinement. It all is about refinement. So the more you can refine, the better. It's funny, I'm trying to read, it's going to take me years to finish it. But The Andromeda Strain by Michael Crichton, Michael Crichton, no, it's fantastic. And it's so much fun reading that book, which is like 50, 60 years old now, and talking about all the mathematical modeling, even in the 50s and 60s, but they're talking about computers that take up the size of a room. It's kind of cute, actually. But it's the same thing. They're doing the exact same thing. They're trying to analyze this alien life form on a re-entered satellite that's causing sickness in this town. But it's all about simulations, because that's all they can do. When you have an unknown event, that's all you can do is simulate what it's already doing and try to replicate that. We did it in 244. The kids just turned in a project last week. But when the BP Deepwater Horizon exploded, about 3 years ago now, it's been about 3 years, in the Gulf of Mexico. And the Coast Guard came out and said, yeah, there's about 1,000 barrels of crude leaking out of that pipe every day. And I'm looking at the YouTube video going, no, it's not. There's way more than that. Way more than 1,000 barrels of crude. So what we did was I took the YouTube video, I talked to a guy down in Louisiana, a physicist down there, who had some really slick tracking software, and from a video, this is badass, you can identify a particle in the video. So like a piece of coral or something that breaks loose and then floats across, or in the case of Gulf of Mexico, a piece of sand or a rock or something like that. And you can track how fast it goes across the screen of the video, and that's a time. And then you can apply a unit of measure to the video. So if you know like how big the pipe is, the pipe's about 14 inches. That's how big the pipe was that ruptured. You can say, okay, that's 14 inches. You tell the computer that's 14 inches. Now it's got a unit of distance and a unit of time. It can calculate speed. So we can figure out how fast the oil's coming out of the pipe at the mouth of the pipe. Then you can say, oh, it's been going for 86 days. The pipe is this big around. It's leaving at this speed. You can get an estimate of how much oil's coming out of the pipe over 86 days. And with 6 data points, only 6, not 1,068, not 10,000, 6, we were able to trap the eventual estimate that BP finally admitted to 86 days later. They finally came around to saying, oh yes, it's this many millions of gallons of oil. But that's not the 1,000 barrels a day. That was ridiculous. It was a ridiculous lowball. But with 6 data points and some really clever geometry, we were able to actually figure out this is how much actually. Now the depressing part about it is, that amount of oil that came out over 86 days is less than 25% of what we as a country use in one.
Wow.
That's staggering. If you add up all the petroleum we use in one day, that's 4 times as much as what leaked out of that pipe in 86 days. That to me is the bigger in the gut. But the fact that you can use mathematics to do something like that, which you cannot do any other way. There's no other way to do that. There's no die to roll. There's no dice anywhere. It's all theoretical. And there's a huge Excel component to that project, which if you guys take it for 244, you'll play with. So, all random numbers. Super rad. Super rad. Yeah, it's good stuff. My God, we got sidetracked today. I love it. Any other questions in here? That's way past what we're doing on Monday. My God, yes. Yeah? Micah, go!
I have a question.
Yes!
Did you draw 242 hearts, or was that it took you 242 draws to get each heart?
No. Good question. You've made a very basic probability question into what's called a geometric probability. And no, this is, I pulled the card out of the deck, looked at it, didn't care if it was a 2 or an ace of hearts. It was just a heart. Put it back, shuffled, drew again.
Okay.
Put it back, shuffled, drew again. Put it back, shuffled,
And
drew
you did
again.
this about 1,000?
1,000 times, exactly. And when I say I did it 1,000 times, I pushed the F9 button, let it run for about 30 seconds.
So that's the probability of drawing that suit on the first draw. 1,000.
It is, every time. Good. Andrew just put out a very good point. This is the probability of pulling these suits on a full deck of cards. Not once the card has been pulled out and removed. That was the discussion we had on Monday about poker, yes? Because it changes depending. For example, if you've pulled all 13 hearts in the first 13 draws, the probability of now pulling a heart has changed significantly. It is now 0 because they're all out of the deck. Which means the probability of all the other ones are much, much higher now. And that's where it gets tricky to calculate poker probabilities, because you have to basically do them as being drawn to. And that's what your exam is going to look like on Monday. I won't give you what are called conditional probabilities, which is assuming I've removed 2 of the clubs from the deck. What is now the chance of getting clubs? That's a great question, but it's also a 243 type. I have a whole project devoted to that at 243. Because it's great. It's fantastic, you know. That's what you look at with false positives. Assuming you've tested positive for the disease, what's the chance you actually have it? It's not 100%. Because you could have a false positive, yes? Which means you tested positive and you might not have the disease. Just like you can have a false negative. Just like you can have a false negative. False negatives you don't hear about as much, which is a shame because you should. If you're getting disease tested and it comes back negative, you should all, I mean, granted, emotionally you're gonna be like, oh thank God I tested negative. But you should also test the false negative rate to see if it came back falsely negative.
Especially a pregnancy test.
Well, I was thinking more cancer. But yeah, I mean, just because I have so many relatives that have had cancer. I mean, pregnancy, yes, of course. But anything, really. I mean, anything, you should always do an error analysis of the false positives and false negatives. Because they're important. I mean, so often, when a test got, I think I told you guys about my overactive thyroid, or my underactive thyroid. Did I tell you about that with my doctor? I didn't. No, I didn't.
Yeah.
Maybe I mentioned it back in the past, right? I tested positive for hypothyroidism. Hypo, which means low energy. Right there, and a whole bunch of other things like unexplained weight gain, sluggishness, all this stuff. And the doc was kind of confused by it. He's like, I'm looking at you, and I'm talking to you, and you're as ADD as the day is long. So it doesn't look like hypothyroidism, it looks like hyperthyroidism, if anything. And I'm talking about, he's like, do you drink coffee? I'm like, a little bit. He's like, a little bit? I'm like, I swear to God, like 2 cups a day. And he's like, okay, that makes sense. If you were hyperthyroidic, you would try to drink coffee to kind of, your body would off-balance it with caffeine. And what we both kind of eventually came around to was, we got 2 routes. We can get you on thyroid medicine. I'm like, for life? He's like, yes. I'm like, let's not do that. Let's analyze the false positive possibility for that test. Because I had taken a whole bunch of tests for him. I had done a liver panel, a heart panel, a thyroid panel, obviously, which I didn't even know about until I went to see him. Whole bunch of tests, all of which came back negative for whatever they had. And then 1 came back positive. And the false positive rate on tests like that should be around 5%. So if I take about 20 tests, 1 of them should come back positive falsely. And I chalked that up to, that's what that was. It was pretty much a false positive. It had to have been. I'm not hypothyroidic. I had just gotten done telling him how I rode my bike to Brockatop, summited, and rode home, and I was still not tired. He's like, yeah, you're hypothyroidic. I'm like, dude, that was to tire me out, and it didn't work. I'm like a Labrador puppy sometimes. So, you can have false positive results, and that's the idea of the last project at 243. So, what do we got? Huh? How we feeling? Hyperthyroidic? I am. Much every day. Till about 8 o'clock at night, then I'm BAM! Out for 6. Pop back up. That's the recharge cycle. Look up to the outlet. Good? Ready for next week? Yes. I'll design this thing at some point today. If I get any clues, if I can email you any clues about what to look for in particular. But I think you guys are ready. Honestly.
Are you in your office right now?
What's that?
Are you going to be in your office right now?
I'm going to stick around. Everybody's got any extra questions? By all means, take off. If you haven't done the survey yet, go ahead and grab a computer upstairs and knock it out. That's great. If you have any other questions you want to stick around for, stick around. Otherwise, we'll catch you on Monday. Yes? Enjoy the early exit of the day. What's the matter, Sonny? Nothing? I'll try to get here at 8. We'll shoot for an 8:15 start, though. There's no reason to have 2 hours. You're not